First thing I want to do is to just review the example problem and the trigonometric Fourier series from the last class. So remember that this is the given equation that says that any periodic signal can be expressed as a DC component, if any, plus the infinite series of cosines and sines where the BK and the AK are determined by these following integrals. Notice that A0, this is the average value of the waveform, and then these are x of t times the cosine, x of t times the sine, where we're integrating all three over one period. So let's move on now to take a recap of the example from last time. Notice this is a triangle waveform, and it's periodic with period equal to 10 seconds, and its average value is 0. So right away we have 2 pi over t is omega 0, that's pi over 5 radians per second, and the average value of the waveform is 0. So we can simplify this x of t by leaving out the a0, putting in our omega 0 values, and we continue from there. Now notice also that we can exploit the symmetry of this signal. Notice that x of t is even, so x of plus 10 is equal to x of minus 10. Okay, that's the condition for an even function. Because it's an even function, we can exploit this simplification that says that bk must be equal to 0 for all k, and so our Fourier series comes down to just simply the infinite series of ak cosine of pi k over 5t. So what we have to do now is to compute ak. So we use the expression that was given, ak equals 2 over t. We integrate over one period of x of t times cosine of pi k5 t dt. Substituting in the values, what we do, it doesn't matter where we could go from 0 to 10, minus 5 over plus 5, 1 to 11. We just have to integrate over one period. Now the reason I picked minus 5 and plus 5 is because of the symmetry. Because we have this symmetry, and again this is still over one period, I can use this simplification for finding AK. Okay, so the even symmetry allows us to integrate over just half the period, then multiply by 2. So instead of 1/5 we have 2/5, and instead of minus 5 to 5 we go from 0 to 5. And the nice thing about this is that in this interval from 0 to 5 I only have one equation to derive. I don't have to do two separate equations. And you can see this is 1, so if we take the y-intercept is 1, and the slope of this we have a 2, it's a negative 2 is the rise, and the run is 5, so minus 2/5 t with the y-intercept of 1. So that's equal to x of t. So if we go back down here to the integral, again, here's where I derive that. So we have this expression. And so you'll have this, the rest of this is just integrating, breaking this up into two integrals. I broke it up into this piece and this piece. And notice that if we go the second term, if we integrate the cosine over half a period, notice that this area adds up to 0. So this term goes away, and we're just left with this term. The next piece is integration by parts. Oh, by the way, this term here is not equal to 0. And you can see that because even though the cosine would integrate by itself to 0, and the x of t, which is the red line here, by itself would integrate to 0, when we multiply x of t times cosine of that expression times t, we get positive times positive for the first half, and then negative times negative for the second half. So that adds up to not be equal to 0. So the next piece is just the integration by parts. You can go through that on your own, and it comes out to be this expression. And if you wanted to write that, again, the final result would be x of t then is equal to the summation k equals 1 to infinity of ak. Let me write it this way, 1 minus cosine pi k times 4 over pi squared k squared cosine of k pi over 5t. So this would be the final answer. And if you wanted to break it out, whether between it's even or odd, you could do that as well. Okay, so that's it for this example.